related rates video 2. So I have our previous examples, like this is levels in a video game, or we're pouring a bag of dirt on the ground and watching it grow, or we're letting fluid drain out of a coffee filter, and this is like 1 second later, 1 second later. This is add a bag, add another bag, add another bag, add another bag, and this is, just playing and getting experience as you go. So the next step before we do our first actual problem is, excuse me, attaching variable names to stuff. So in this case, I might use the letter L for level, right? So like if I were positioned right here, this would be level equals 9, right? I know that's very obvious, but that's not the main part. What if I wanted to talk about how fast you were cycling through the levels or increasing your levels? How would I articulate that? I just said it in English. How do I say it in math? It would look like this. dl dt. Now this is hugely important. Actually, we probably wouldn't use t for this, but I'll make up a scenario. Excuse me. So if we were playing a game continuously for like 5 hours, then I could think of this as like time. And in the first hour, maybe I got through to level 4. In the second hour, I almost got to level 6, right? Like that. So how fast, this means how fast is the level changing as time. I'm going to put passes, but I'm going to put changes. Right? These are our two variables. How fast is the level changing as time passes? So see what the variables mean in that notation? The d something, that shows rate of change. It also happens to be a derivative. The d, the black ink right there, is showing rate of change. How fast is this changing compared to that? How fast is this changing as time changes? Let's look at this one. So I might say for my main variable, h equals height, right? So this would be height equals 3 feet. This is height 2 would be like 5 feet. Height 3 would be 6 feet. Height 4 would be 7.5 feet. And I could say like height equals 8 feet or whatever, right? That's what it is. But see how each bag, the height is growing slower? How do I articulate that thought mathematically? Well, d something means change in. How fast is it changing? And I want to know how fast is the height changing per, now this is a weird one, per bag. What is d height per, what is d height d bag? That's really weird. Like we wouldn't do that in a math problem. I'm just trying to get at what this stuff means. The d something over d something means change in. And it's like there's always two things involved. How fast is the height changing for every bag that gets added into the mix, right? How fast is the height changing? The way I would word this, like mathematically, like using English, I'd say, how fast is the height h changing with respect to the number of bags. With respect to means, now I'll normally abbreviate that WRT, with respect to. That means how How fast is changing relative to the number of bags? How fast is the H changing per unit bag? But with respect to means compared to, measured against. Again, we're getting into more abstract things, but if you're going to go to the next level, you can't just think about one thing, height. You've got to think about height as it relates to something else. It just is how it is. Like, the more sophisticated you want to get in how you analyze what's happening in the real world, you can't always have it in one variable. And you've got to talk about how they interact with each other. And that's what these are, related rates. The rate at which one changes is related to the rate at which another changes. They are related to each other. Okay, so that's actually going to apply a little more later, but let's keep going with the notation. So if I want to say what's the height, I say h. If I want to say how fast is the height changing, I use this derivative notation. Let's use the coffee filter. Instead of h, because I already used h there, let's call it depth. Depth 2, depth 3. Oh, bad. Let's call it capital D for depth. So if I want to know the depth, I would say D equals, maybe it's like 3 inches, right? The depth is 3 inches. If I want to know how fast the depth is changing every second, it's different. Like, this might have dropped 1 inch in a second, and this might have dropped 3 inches in a second. The way I articulate that thought is D, T. I want to know how fast the depth is changing over time. I want to know how fast the depth is changing with respect to time. I want to know how fast the depth is changing per unit time, per second. Okay, so that's kind of the notation. So I'm going to just set up the next problem, and then in a video 3, we're going to solve our first problem. But this just takes a lot of work. So where are we at? We're at 7 minutes. So a conveyor belt dumps dirt or sand on the ground. At a rate of 7 cubic feet per minute. That would be the correct units there, or some correct units there. The sand forms a cone-shaped or conical pile on the ground whose diameter is 3 times its height. So as it falls and forms the pile, it's going to be more spread out than it is high. How fast is the height of the pile growing when the height is 4 feet high? So here is a very standard problem. You'll see this in lots of textbooks, ones like it. The numbers will be different. And I just want to pull your attention to this question because I know that's going to be strange when you read that. How fast is the height of the pile growing when the height is 4 feet? See, if you read this at a surface level, you're going to have problems. If you're just skimming it and you're just seeing the word height, then this is not going to make a lot of sense. how fast is a word that means rate. How fast something is happening. How fast is the height of the pile growing? Growing is a form of changing. It's not static. It's not constant. It's growing. So all this red line right here, that is one idea. When the height is 4 feet. That is a separate idea. Now, think about the picture that I had drawn. I got to put caps on these because they're running out. When the pile is 1 foot high, now I'm going to add another bag, and maybe it's 2 feet high, and then I'm going to add another bag, and then maybe it's 2.5 feet high, and then I'm going to add another bag, and maybe it's 2.75 feet high. See, the higher it gets, the slower it's growing. If I would have said, how fast is it when it's 1 foot high, the height would have been growing faster than when it's at 4 feet high. And it's going to be growing even slower when it's 10 feet high, because think of all that dirt that's got to spread out over the whole pile. So not much of it is going to be going towards the height. So the actual rate that the height is going up is slowing down. See, these are two separate ideas. And this is the point in time when I want to ask, well, how fast is it growing then? How fast is it growing then? How fast is it growing then? See, I got to pin that down because it's changing. It's not the same all the time. All right, so having said that, how do we solve these? I'm going to very briefly write the procedure down here. You're going to want to pull up the notes that I make that give this procedure. But this is going to be super brief just so we can keep track of it. This is not a thorough explanation. So our procedure, here's the problem. When possible, draw it. I know some of you will want to not do that, but you're in for a world of hurt if you won't do your drawings for related rates. So draw, if possible, draw it, and we can draw this. It's a cone-shaped pile. Guess what we got to draw? A cone. Okay, so first we're going to draw it. 2, put variables and constants into the drawing. So in this, if we're using, like, let's take the easy one, height. I'm probably going to be using h for height in this math. So I want to put the h in the picture so I can see how it works. 3, identify or create equations, usually 2 of them. So we're going to need equations. I'll tell you in this one of them is going to come from this statement right here. And the other one isn't even listed. The other one you have to realize you need it. And we're going to talk about that in video 3. You are not going to like that. We are turning the page here where you have to start deducing and concluding what is appropriate in a problem. All the math is not going to be fed to you. What we're doing is we're starting to be able to assemble pictures from all the stuff we've been learning. All right, so I'll be more thorough about that in the next video, where we'll actually solve this problem. Right now I want to list the procedure briefly. 4, this one's not going to make any sense till we get to the next video. Reduce the variables in the main equation to 2. So if there's like 3 different variables in our main equation, we got to get it down to 2 variables in the main equation. That's really important. 5, plug in all knowns. Oh, no. That's bad. I'm going to run out of room here. 5 is take the derivative. You've been seeing that we use derivative notation, d something over d something. At some point, we're going to have to take a derivative, and I do apologize for this, but it's going to be printed out. Number 6, plug in the knowns and solve, right? So that's pretty, I don't like how that's positioned. In the notes it'll be clear, it'll be all laid out vertically. So we want to draw it. We want to put our variables and constants into the drawing. Where are we getting them? From the reading. We have to identify or create appropriate equations from what I'm reading. We have to reduce the number of variables in the main equation, whatever that is, down to 2. Then we're going to take a derivative, calculus, and then we're going to plug stuff in and solve. So we're going to try to figure out how to do those words to this problem in the next video.